Professor Strauss from Brown University in the United States. And the title of his talk is Upper Bound on the Slope of a Steady Water Waves. Please.
Thank you. It's a pleasure to be here. I want to dedicate this lecture to the memory of Kathleen Morowitz, who just died on Monday. She was a great mathematician. I worked with her. It was a wonderful part of my mathematical life, and she was a very important person, a real applied mathematician, and I was kind of shocked that she just died this week at the age of 94. So if we all lived to 94, it's not so bad. I mean, okay. Okay, so I'm talking about how steep a wave can be under very special circumstances. So it's a steady 2D water wave, like there's several talks here this week on those kinds of waves. So at first I thought I'd show some physics. These are actual waves in an ocean or something. This is from Van Dyck's book, well-known book of pictures. And here's another crazy picture. It shows how crazy waves can be under some circumstances. Not exactly what I'll talk about, but you see, you get all kinds of overhanging and vertical. What I'm going to talk about is the slope. So you see, the slope can be vertical. So here's what I'm talking about. So first of all, I want to say I'm talking about joint work with Miles Wheeler and with Seung So. Seung So is way back in the last row, and very few of you know him over there. Why don't you just wave so people see who you are? There he is. Okay. So I'm going to consider okay, so it's a steady 2D water wave with flat bottom, free surface, pure gravity wave, no surface tension, incompressible, no viscosity, and I'll talk actually in this talk about periodic waves, but these results are also true for solitary waves, and they're symmetric around the crest. So I guess there've been a number of talks here on that kind of wave, and there's just air above with a fixed atmospheric pressure, P ATM. Okay, there are many such waves. I think this audience knows very well there are many such waves, and so here's a little picture of what I'm talking about. Periodic case, gravity points down, y is up, and eta, the surface is y equals eta. And so what's the angle of inclination? So I'm talking about how steep it can get. So I have it pretty steep right there, but that's the question. So I'll call theta the angle of inclination with respect to the horizontal. So the extreme Stokes wave, the one from around 1850, where the famous one, you talk about a 120-degree angle. There's a corner. There's a 120-degree angle below, but I'm talking about the angle of inclination with the horizontal. So it's 30 degrees. That has 30-degree angle, and it was known by Stokes, but not proved until rigorously until much 20th century. And that Stokes wave is irrotational, but and so in the irrotational case, it was generally assumed that all of these waves, even not the extreme Stokes wave, but the others, all have angle less than 30 degrees. And if you do rough numerical calculations, it looks like that. But in fact, the more delicate theoretical numerical calculations near the Stokes wave showed that the angle is bigger than 30 degrees when you're very close to the extreme wave. That was quite surprising. And then that was proven that the angle can surpass 30 degrees by McLeod, I think in the early 80s, I believe. And then Amick in 1987 proved, it was a really remarkable paper, proved that the angle, even though it can surpass the 30 degrees, must be less than about 31 degrees. So here's Amick's paper. And Amick, so this is irrotational waves, and it starts right from the beginning with the Nekrasov equation. Nekrasov equation is a way to go to completely write the equation on the surface, on the free surface. So it used the fact that the wave is harmonic inside the fluid. Okay. So when you have rotational waves, which means vorticity non-zero, there was nothing known until recently at all. So nothing at all. And there are some examples which we did know, like there's the Gerstner wave, the extreme Gerstner wave, has a cusp. This is from 1802. That has a cusp, and so it's vertical. The angle is vertical. And there are all kinds of numerics that show that if you have sufficiently adverse vorticity, which by vorticity, if you have sufficiently adverse vorticity, which is large enough, then you get vertical angles, and also overhanging and so on. But if you have favorable vorticity, so favorable, the way I define vorticity, favorable vorticity means vorticity is negative. I'll be more specific in a moment. So if you have favorable vorticity, Miles, Wheeler, and I prove that you get at least an upper bound of 45 degrees, which is nowhere near 31 degrees, but it's an upper bound because it wasn't even known that before that you don't have vertical, that the wave becomes vertical somewhere. And we show that we have a restriction. This is true. The restriction may exclude some of these waves, but numerics, very recent numerics by Katie Oliveras, indicate that probably our theorem is valid for all such waves, not just a large class of favorable vorticity waves. And then, in a more recent theorem by Seung and me, we were able to show that if the vorticity is adverse, but not too big, then we get the same kind of result. We get an upper bound on the slope. Now, Amick's proof, the proof in that paper that I indicated to you, doesn't generalize because he uses the Nekrasov formulation, which he basically uses strongly that you get a harmonic function inside the fluid. And also, he's able to use complex analytic functions and using techniques from there. And I should mention that Plotnikov and John Toland also have a proof of a similar result to Amick's by a somewhat different method. So here's a picture of our wave, the same picture as before. So that's what we're talking about. I'll assume it's periodic, the period L. And okay, so here I'm writing down the model. Now, I think probably this week you've seen these equations many times. I'm assuming it's two-dimensional, so the vertical is y, and I'm taking a moving frame. So if you look at the top line there, I'm taking a moving frame, so when I write x, I really mean x minus ct. C is fixed, it's a traveling wave with speed c. And when I say u, I mean, I don't know if you can see the red dot. You take u, it really means u minus c, but it's easier to write u and easier to write x. Okay, then the traveling wave looks like a stationary wave, and so yeah. So you have divergence. So and the other thing is u with an arrow. I just write it two components, u and v. So there's the Euler equations, steady Euler equations over there, and then on the surface it has two boundary conditions, which you've seen before. The pressure is constant and v equal u eta x. Eta x is the slope. And the bottom, you have v equals 0. And then you can define a stream function over here. So defining this stream function and the vorticity defined this way, it's a scalar. I notice I write it this way, so that favorable vorticity is when this is negative. And that's equal to a function of psi. So you get this equation for the stream function. Okay. Okay, so now I think you've seen this before. So now there's existence theory. Well, I'm not going to spend any time on this. You have lots of those waves. So actually, it began all the way back. Theory of these kinds of waves went all the way back to late 18th century. And there's a whole curve of wave. Maybe I don't have to repeat this because it's been done this week. There's a whole curve of smooth periodic waves. You actually see infinity periodic waves of this type with any choice of vorticity function. Okay. And these waves all satisfy this curve of waves satisfies this, but this is really means u is less than c, this condition. Okay, so there are lots of the waves. Here's a picture of a numerical picture of here's what they look like. They bifurcate from flat case, and you get things like that. That's one period. Okay, so here's the theorem with Miles-Wheeler. So the assumption I want to, the assumption I want to emphasize is, what did I do there? I did something wrong. Oops, I didn't want to go that. I'm going backwards, forwards. Okay, there. Okay, there. The assumption I want to emphasize is that one over there. Assume that gamma is less than or equal to 0. Gamma equals 0 is irrotational. Gamma less than 0 is what I call favorable. And also a couple of conditions on this derivative, but gamma could be a constant even. That's a non-trivial case. And the third line of the theorem, u gamma, so is the restriction. So at least until you get to u times gamma equal g at the trough, at the lowest point, at least until then, all the waves in the continuum solutions have angle less than 45 degrees. So the trivial wave satisfies u times gamma less than, so u is negative, gamma is negative. U times gamma is positive. It means that gravity is dominating. That's the condition. So as I mentioned, Katie Oliveras has numerics. And in her numerics, that condition is always satisfied when she computes. So it seems to be true, but we haven't been able to prove it. That is always true, but anyway. So it starts out with a trivial wave, satisfies that condition, and then that condition definitely holds for a long part of the for a lot of the waves, for quite a long distance, and maybe forever. The same, there's a variation of this which works for solitary waves. Okay, so that's the theorem. I'll state it a little more precisely. Now I'm going to say it a little more precisely, restated. So I'm going to say a little more precisely, so you don't have to talk about the existence curve. Just take any collection of these waves satisfying the conditions at the top. These are, take any collection of those waves which is connected in function space, and connected in function space, and assume that this connected set of waves at least contains a trivial wave. And then if all these waves satisfy this condition, then the slope is always less than 1, meaning the angle is less than 45 degrees. So that's a little more general, precise statement. Okay. All right, so the proof. So this is just a couple of comments about the proof first. The proof uses a number of identities which are not obvious, and it uses the maximum principle strongly. So the key to the proof is that du dx, that's u sub x up there, du dx strictly has a sign. It doesn't vanish. And what it actually means, what that thing, this is part of the proof, is that the water is flowing faster when it's shallow. So you have a wave like that, and where it's shallower, the water moves faster, and where it's higher, the water. That's what that inequality means. So that's part of the proof. We have to prove that as part of our proof. And we also use the Hopf maximum principle in a couple of tricky ways, particularly to this quotient, du dx over u, and this quotient, v over u. V over u is the slope. So we use the maximum principle quite strongly. And, okay, so, so we look at different regions, and we want to see how steep it can be. Let's see, I think I want to, okay, I'm going to skip that. I want to state the other theorem, the theorem when you have adverse vorticity. So I'm going to go a long way here. Oops, not that far. Here, the theorem with adverse vorticity. This is the theorem with Seung, so very recent. So this says, notice, I have no assumption here about the sign of gamma. It could be positive, negative, but you think of it as being positive because that's the case not covered before. And it says if gamma, the vorticity, is sufficiently small. Now, there's an inequality which is sort of messy, but if it's sufficiently small, then the slope of any wave in the continuum the constructed continuum, we know, this is the constructed waves, we know about those, that the slope of any such, if that's small enough, then the slope is less than, well, a little more than 1. So think of delta as being maybe a small number. Think of delta as being, it doesn't have to be small, but think of delta being a small number, so we don't prove it's less, the angle is less than 45 degrees, we prove it's less than 46 degrees. But we have a bound. There's a bound, and I repeat what I said before, that if you have adverse vorticity, gamma positive, and it's big adverse vorticity, then there's no bound. Then we know it becomes vertical. This is certainly obvious from numerics. So this says if gamma is not too big, you still have bound, which is not surprising intuitively, because when gamma equals 0, you have a bound of about 31 degrees. So it's not surprising, and certainly we would definitely like to improve this, the number, but this is a beginning. So I'd like to emphasize, I'd like to continue with the part of this proof that's really different from the other proof. And let me pause here if there are any questions.
Gamma is small. How small is the?
Sorry, gamma is what?
Gamma you said is small, sufficiently small, but how small is in the?
Oh yeah, okay. I can be specific. If you want to see how small, I'll show you that in a moment.
But here you have also unidirectional flows.
Yes, going. Yeah, you have a speed c for this wave. Yeah, c is a constant. I usually think of c as positive. Yeah.
So in this statement here, you don't need any assumption about the u like you had in the previous theorem. So u gamma less than g. Here it seems like you don't have.
No, there's no condition. So in the first theorem, I was talking about favorable vorticity, but vorticity could be large. I mean, in magnitude. That's where I need that condition. But yeah, so I didn't say it before, but if gamma is sufficiently small in magnitude and negative, then I didn't need that extra condition at all anyway. So when gamma is negative, this theorem was known. When gamma is negative, this theorem appeared in my paper with Miles Wheeler. Yeah. Okay. Well, let me tell you the guts of the proof, and then at the end of the proof, I'll give you an inequality which says how small. It's some messy thing. Okay, just comes out of the proof. All right, so I want to show you the new lemma. So this theorem uses a lot of the techniques of the paper with Miles Wheeler, but there's a new part, so I want to emphasize that. So the key new lemma, so now consider gamma positive. It's going to be small, but so far it's not even small yet. And it says take the wave and look along the wave where it's steepest, at a point along the surface where it's the steepest, and call such a point M. Assuming the solution is smooth function. So call that M, and so that I use X, so that's capital M. It's a point in XY plane. On the surface, slope is biggest, and then the lemma says that if you have the same condition about the speed of the wave that we had before, and if you also have this condition, which is like that, similar to the condition before, this says gravity dominates. This says gravity is dominating that term gamma. See, gamma here is positive, and u is negative. So this says again that gravity dominates. If that's true at m, then you have a bound on the slope, this thing. And given that condition, this quotient, both positive, it's a quotient of two positive numbers. It says that there's a bound on the slope. So after this lemma is proved, one has to prove that if gamma is small enough, then this is true and this is true. But here's the key lemma, the key idea. Okay, so so we write some identities along the surface. So pressure. Here's pressure on the surface. This is the notation for the surface. You just differentiate the pressure along the free surface, multiply by u, and then you do the calculation from the Euler equations, and you get this. And I used the boundary condition. So if you do, you get, for example, the derivative of eta, but the derivative of eta is v divided by u by the boundary condition, and then we have the Euler equations. Euler equations say that the partial derivatives of the pressure are equal to something, so I eliminate the derivatives of p. Anyway, you get this exactly on the surface. This is on the surface. Okay. And then we also can eliminate derivatives, all the derivatives of v. V is the vertical component of velocity. So you have derivatives of v here and here. And I can eliminate them by using incompressibility and the rotational, the vorticity, and then that same equation just becomes equation 10. Okay. This appears in the earlier paper already, but it's used here in a different way. Now consider the slope. I'll call it S, just S for slope. And the slope is equal to derivative of eta dy dx. And this is the boundary condition, v equal eta prime u. So that's just notation. And now you do a calculation, which is really not obvious. And S, you just do a calculation with S and you do the same kinds of substitutions. But it's not obvious at all, I must say. And you find that S satisfies that equation. Now there are derivatives of S in a couple of different places and some other stuff, but you have just the regular Laplacian of S in the plane, and then you have a horrible coefficient times Sx and a horrible coefficient times Sy, but that allows you to use the maximum principle because there's no term, the way we write it here, there's no term with S. So you can use the maximum principle. So we use the maximum principle, and S, positive or negative absolute value of S, has no maximum in the open set by the maximum principle. And then you look, so we look at, so you have the wave, I look at here's the crest and here's the trough, and I look at this part of the wave, and S plus is the part of the surface, with this part of the surface. On this part, that's the plus. And then you have a distorted, the surface here, and then you have three other parts. You show that the maximum cannot happen on the three other parts, so the maximum must be at some point on the surface. So I'll call that M now. And all we have to show the bound on the slope at this point. That's the point of maximum slope. And now we take such a point. We take the point of maximum slope. Well, the second derivative of eta has to be 0 because it's the maximum. Maximum slope, the slope is eta prime. So you take first derivative of eta prime has to be 0. Okay, at that point. Now we're going to just do at that point. So along the surface, we have along the surface is the boundary condition. We can differentiate it along the surface. We get this. But the last term, second line, the last term is 0. So we can throw that away now at the point. And then we can rewrite that according to the fourth line there. It's just another way to rewrite it using the letter S. And then we can also say V equals SU, so we get rid of V and we write. So we get it according to this middle line here, this one. So we get this. This is actually a quadratic equation in S. And now you can, now we look at the two displayed equations. And we have uy in both equations. And we can eliminate uy. You eliminate uy, it's simple. It just, uy just appears linearly in both equations. And then what you get is this equation in red. So that just comes from the above. And this equation has no uys in it. And now you have a fourth order equation here in the S. You have S's appearing with all kinds of coefficients. And yeah. And now we are assuming we are assuming u is less than 0. That means no stagnation. And on this part of the on this part of the curve, S plus, S is negative on this part of the surface, and this is negative, and this is one of the assumptions of the theorem. And therefore, you look at the signs of these terms. You wouldn't think you could get much out of this, but you look at the signs, and you notice that this is negative, and then you have positive coefficients. So this first term is negative, and u times s is positive, and therefore we conclude that the part in the square bracket must be positive at the point M. And we assumed, the other assumption we made was that G dominates this and G dominates this. So these parentheses are positive. And so therefore S squared is less than this quotient. That's the conclusion, that's the lemma. Now, okay, so I didn't give a proof of the favorable case, but yet anyway. But okay, so let me go back to this is in blue. That's what I've just proven, and what we have to do is those two hypotheses. We have to somehow prove those two hypotheses, assuming that gamma is small. I haven't used gamma small yet. Okay, so the first one is ux less than 0, which I talked about before. So what I would say is a rather intricate argument to show that us is less than 0. It works the same way as in the favorable case, which I haven't shown you yet. And then we have to show also that gravity dominates. And then at the end, we have to show that that funny quotient is less than what I call 1 plus delta, provided gamma is small enough. And if you look at, if we assume for a moment that ux is less than 0, and we have to prove this and this, then this inequality just combines the two other inequalities involving G. It combines it, so we have to show that's this inequality, the displayed one. And this display, it's very easy, you just, for the flat wave, it's easy to see that this is true. For the wave where you bifurcate from. And now, and so, yeah, so I'll skip. So now you have to say that if gamma is small, in some sense, then that inequality is true. So here's the inequality, which this is a sufficient inequality on gamma. So given delta, given the mass flux m, given gravity g, the right-hand side is a constant. Think of delta as small. And then on the left side, you have gamma cubed plus something times gamma squared is less than that. So that something is also just constant. L is the period. And therefore, therefore gamma, this is some inequality on gamma. Gamma is small enough. This just comes out of the proof. I'm sure gamma could be much bigger. Okay, so that's the proof of the theorem, of that theorem. Let me see, so I have plenty of time, but let me give open questions, and I can go back and talk about some other things that I skipped. Question one is this gravity domination, is this true? Can we prove that G bigger than U gamma is always true along the whole continuum in the favorable case? So this is what, as I said, the numerics indicate that it seems to be true. In the adverse case, we know that if gamma we now know that if gamma is small, we get the upper bound and upper bound. But if gamma is big, we know we don't clearly from numerics. But where's the transition? How big does gamma have to be to how big can gamma be until you get a bound, until finally you get a bound where it becomes infinite? You can also ask about specific angles, but I think most interesting is when can you have waves that become vertical somewhere? And we have technical conditions. These are, I consider point 3. These are technical conditions, I think, but we need them in the proof, and I don't know how to get rid of them. I suspect probably one of maybe the second one is not necessary at all, but the proof needs it. In the favorable case, or even in either case, can we make the angle closer to Amick's angle, 31.15 degrees? I don't know how to do that. And 5 is really a conjecture. Maybe this is completely crazy. But if we're in 3D, well, you don't have one angle. You can look at all the different directions. So I'm talking about some people call a two-dimensional wave. The surface is two-dimensional. So, for instance, you could ask the question, if you have an irrotational, maybe the answer is no, I don't know. If you have an irrotational 3D steady wave, Well, there are not so many 3D steady waves, but there are some. Maybe all the slopes are less than 45 degrees. And maybe someone in the audience has some insight on that. I'd like to hear people who've worked on fully three-dimensional waves. Okay, so there's still a few minutes. Let me pause and then I can go and fill in some of the details that I skipped. Are there any questions at this point?
Could I make a remark about the vertical question, question 2?
Sorry, I can't hear you.
Question 2?
Oh, question 2.
Vertical.
Yeah.
The very first proof in the irrotational case that a Stokes wave is the graph of a function is due to Spielvogel in 1973.
Who?
Student of Spielvogel?
Oh, yeah. Spielvogel. Yeah, that's right. Yes.
He used the fact that...
We looked at that. Yeah, it was very useful.
Look, he used the fact that the pressure is a subharmonic function which is constant on the surface. That was the key ingredient. But what I wanted to say was that the argument is not local. It's not about there being a single point where it's vertical. It's more subtle than that. It's a global topological argument on the shape of the surface. And I wondered if you can use that in this more complicated situation.
Well, we were looking at Spielvogel when we began the whole problem before we proved anything. So I'm not sure. I'm not sure if it's totally rigorous, but it gave a lot of insight for sure.
There are rigorous versions of it nowadays. It has been made rigorous.
Yeah. We're well aware of Spielvogel's result. Yeah. Hisashi?
Number 3.
Yeah.
I'm not sure if I remember correctly, but the toroidal wave, Gerstner's toroidal wave, I think it is minus on the free boundary and go to 0. So it is increasing, I think. So if gamma is increasing, toroidal wave can be very steep. So I need...
For the Gerstner wave.
Gerstner wave. So if gamma prime is negative, or then if this is conditionally removed, then it might be very difficult.
Maybe. Gerstner wave, I didn't mention, Gerstner waves is infinite depth,
Yeah.
so it's a little bit different. But yeah, maybe. But I mean, it's funny when you look at the proof, I haven't shown you that part of the proof, but these two conditions just occur like, it's just, you have identities, and there's one term you got to get rid of, we don't know how to get rid of it. So unless we assume those, there's one term to get rid of that, and there's another place we use that, we have to get rid of that term. So it's just, it looks like a technical part of the proof. Adrian?
Can you use this to get somewhere a lower bound on the slope?
Oh, a lower bound.
Not
We
zero,
didn't
but
try.
to say that somewhere along the continuum, these waves will have a slope like bigger than 15 degrees or something like that.
Oh, we didn't, I haven't thought about that. That's a good question.
So this is a theorem about these curves on this continuum. But can you hope that the theorem like that would hold for all states, not necessarily
Yes,
for
maybe.
to the...
Yeah, it's another good question.
The argument didn't depend.
Amick in that paper for irrotational waves, he proves it first he proves it for the continuum, and then he does some other intricate argument, and he shows it's true for all waves, basically. And then it's a very intricate argument, and he uses heavy use of complex variables in that paper to get all the way down to about 31 degrees. So, but yeah, it may be true not just on the continuum of solutions, but others, maybe all solutions. So in the favorable case, I wouldn't be surprised if in the favorable case, It's true for all solutions. Yeah, without any, yeah. So our theorem, the theorem in the favorable case said you don't have to be on the continuum, you can be anything, but we have that funny condition that gravity dominates. And the numerics of Oliveras, when she calculated these things, show that gravity, show our calculations of the continuum. But of course, we don't even know what all the steady waves are. That's an open question. What are all the steady waves? Even in 2D steady waves, what are all of them? Have we got all of them? We don't know that.
But you don't need to know whatever the piece.
Yeah, I know. But if you do numerics, you got to put your numerical fingers on some solutions. And we don't know if we have all of them. So she calculated, starting with the standard continuum, and the inequality is always satisfied in every one of her calculations.
If gamma, for example, is a constant, can you say something?
But gamma is a constant.
Yes. Can
Yeah.
say something more, or this is...
Can say something more. Well, when we did this, the thing we were thinking about mostly was gamma equal constant. It's kind of amazing that even when gamma is a constant, which is such a simple case, it's really so different depending on what gamma is. So we did the whole thing. In fact, we did the whole proof gamma equal constant, and then we said, well, we don't really need gamma equal constant. I mean, when gamma is a constant, the proof is basically the same. It hardly changes. We did gamma equal constant, and then when we took gamma not constant, you know, we had a few extra terms we had to play with. But yeah, I don't know. When gamma is a constant, maybe you can use conformal mapping techniques to improve this. That would be probably a different kind of proof. You can take gamma equal constant and sort of subtract it off and consider the difference. That's a possibility. I wouldn't be surprised if you could do something special when gamma's constant.
And when you have these inequalities, I mean, the mean depth, does it matter whether it's get big or, I mean, but I
Well,
mean,
the depth, what I've done is, what we have often done is take the flux fix rather than the depth.
Okay, but is there a limit where things are better or not?
I haven't investigated how it depends on the depth. Yeah, it might be interesting to see how does it depend on depth, and particularly question 2, there's a transition of when the slope becomes really big. There's some transition point, and then how does that depend on the depth or the period or various other parameters, particularly the depth. We have not tried to investigate that. So I've omitted the, I really haven't given you the proof of the favorable case. Maybe I'll just give you a glimpse of that proof, of part of that proof, which is also part of the proof of the adverse case. So let me go back. That's some of the things I skipped. I don't know. Oh yeah. So I want to. Yeah. So for example, so in part of the technique. Yeah. So there's a lemma. Now we're in the favorable case. I just give you a glimpse of this. Favorable case, and we take solutions with ux less than or equal to 0 on the surface, on S plus part of the surface. And one of the conclusions of lemma 2 is that actually you cannot have an equality. And then there's another conclusion which is really technical, which is important for the proof, but let's focus on part A. So this I already showed you before. It's the same thing. Differentiate the pressure on the surface, and then it simplifies to this form. And then we take a second derivative on the surface. So we take derivative on the surface and then another derivative on the surface. It's a mess. But it's not, well, it's in a lot of terms. What are there, about 15 terms or something like that? Equation 5. So on the surface, the wave looks like satisfies that equation where we've done some elimination of certain derivatives of v. And then key technique is we look at this quotient. So we want to show that something about the sign of this guy. We're assuming the sign of this is negative. And we want to show, and we're assuming the sign of this is less than or equal to 0, but we want to show it's less than 0. And this is the slope. And as I sort of indicated a little bit before, you have an equation, well, similarly to what I said before, you have equation 6 for the quotient ux divided by u. And you have a similar equation for the slope. Oh yeah, I think I showed you 7 before, but I haven't showed you 6. Both of them you can apply. So you can apply the maximum principle in both cases, except in equation 6 you have that nasty term on the right, which is killing us. So we say, oh well, let's assume gamma double prime is less than or equal to 0. So we throw it away. Now you can apply the maximum principle, maximum or minimum principle. So that's the only place where we need gamma double prime less than or equal to 0. That's why I think, I don't know, I just have a feeling you probably don't need that condition. And then we apply the maximum principle. And okay, then we apply the maximum principle. Let me skip a lot of stuff. So, so the maximum, so then we know the then we look at the three other sides, and then we find that the minimum of, so in red there, so we show from the maximum principle we show the minimum of ux divided by u, that quotient, is achieved on S plus, on the top part of the surface from crest to trough. At some point, and then let me skip some of this. I'm just giving you a little bit of an inkling of what we have to do. And then we eventually show that at the point where ux divided by u, I'm calling w, at the point where w is maximum, we prove 9. Oh, nice quadratic inequality. But A, B, and C are those things up there. It's a mess. It's quite surprising you can get anything out of this. And therefore, and now you look at the signs of the various things. And from when you look at the signs of these things, so when you look at the signs of the various things in A and C are positive if you check the signs. And then but you have here, C is positive, A is positive, and you have this. And and W is less than or equal to 0. But because this is strict and this is strict, and therefore W at Z0 cannot be 0, cannot be equal to 0. So, and so we assumed that this was less than or equal to 0. And so we've just excluded W being equal to 0, which was this lemma. That's part A of the lemma. So it's a rather intricate argument. It's not clear how you generalize very well. But so I've left out some other parts of the proof, but that gives you an idea of the favorable case, and then a lot of the ingredients of the favorable case, I said we also use for the adverse case. Okay, thank you very much.
Is PD for various computations for constant vorticity, or does she vary vortices where she calculates the slopes? Is that
Well, I don't remember exactly. It's not yet published.
yeah, I would imagine. Yeah.
So she definitely did constant, and I think, well, she certainly can allow variability. It's no problem for her. She did various computations. Yeah,
Yeah, with my son, I know.
I mean, yeah, I don't know exactly the status. I've been asking her to please write it up and get it written up so I know exactly. But yeah, I'm not sure. But she did a number of quite a few cases with a large gamma, small gamma, and so on. And that inequality is always satisfied in the favorable case.
Thank you.
Yeah.
Any other question or comments? Ask one question. I'd like to know the sign of the inward normal derivative of the pressure P on the water surface. So
The sign of the what?
inward normal derivative.
Inward normal derivative.
of the pressure P.
Yeah, question that's related to whether you have a pressure sink.
Yeah.
Yeah, that's right. We have one thing we proved, something I skipped. I'm trying to think where I found that. Maybe it's here. Let me see if I can find it. I'm skipping a lot of stuff here. No, I'm not sure if I have it here or not. Damn. Oh yeah, right. Okay. Miles Wheeler and I show that under some conditions there's no. We show that. So maybe I just skip this. We show that that if a wave overturns, rather general statement, if a wave overturns, then there must be a pressure sink, meaning that derivative has to be
Negative.
the pressure is smaller somewhere inside than on the surface. That's a relatively general statement. Yeah, and also Adrian has also a proof of that. Other than that, yeah, that's a really interesting question that could also be investigated numerically. Like, when do you get a pressure sink? And even if it's true that an overturning wave has to have a pressure sink, but can you have a pressure sink when it doesn't overturn? Do you know, Andre?
Well, no, that's something interesting. It's like a little bit also in terms of stability of these, which was in my mind. I was going to ask stability of these traveling waves, right? I mean, there's a point that here it's steady, but then when you let it loose, right? Then yeah, I don't know if I know how to answer this.
I think there are a lot of interesting questions.
Questions to be explored. Yeah.
Yeah.
Let's thanks to the speaker again.